Advanced Encryption Standard. In this session, we will understand the basic overview of how AES works. Before diving deep into AES, let us understand the prerequisite. The first operation is XOR, which operations plays a vital role in AES as it is used in the key scheduling algorithm and encryption-decryption process. Moreover, it is extensively used in mixed column operations for modular reduction and polynomial multiplication. We will discuss all these operations related to AES such as mixed column, key expansion, etc. in upcoming sessions. Just remember, for an odd number of ones, XOR outputs high, which is 1, otherwise, it outputs low, which is 0. Another important thing to note down is that each byte is represented in hexadecimal notation. Moreover, in this case, we assume that one word is equivalent to 4 bytes. One of the most important things to consider is that it uses a 4x4 matrix which is equivalent to 128 bits for generating the cipher text. The matrix is filled in column-wise for performing AES operation. The key which is used for encoding to generate a cipher text can also be used to extract the plain text, and as we use the same key for encrypting and decrypting, therefore it is called symmetric key encryption. For example, let us consider on how AES-128 secret bit is represented using a 4x4 matrix. Let the 16-byte secret key be, that's my kung fu. The hexadecimal notation of the ASCII code of the letter is obtained first, then it is filled column-wise. Similarly, AES-192 secret bit message is represented using a 4x6 matrix initially, and AES-256 is represented using a 4x8 matrix initially. Key scheduling. Whether you are encrypting or decrypting, this is the first process of AES, in which the cipher key is expanded, and a multiple round keys are generated including the cipher key, which is used in encryption and decryption process at specific rounds. The process involved in key scheduling are round constant, rot world, byte substitution, the key size, the total round keys including the key, and the number of round constant for key expansion. For AES-128, 192 and 256 are provided in the table below. Here W represents words. Let us visualize the key expansion of AES-128. Here 10 rounds of key expansion are performed and 10 round keys are generated with a total of 11 keys. Now for AES-192. Here 8 rounds of key expansion are performed and 12 round keys are generated with a total of 13 keys. Now for AES-256. Here 7 rounds of key expansion are performed and 14 round keys are generated with a total of 15 keys. AES Encryption. This is performed after key scheduling, where the round key is generated, which is used to convert a plain text into cipher text. The process involved are byte substitution, shift rows, mix columns, and adding round key. In the next slide, we will visualize AES-128 encryption, which consists of 1 initial round, 9 intermediate round, and 1 final round. Similarly, AES-192 include 13 rounds and AES-256 include 15 rounds. AES Decryption. Just like encryption, this too is performed after key scheduling, where the round key is generated, which is used to decode a cipher text into plain text. The process involved are inverse bytes substitution, inverse shift rows, inverse mix columns, and adding round key. In the next slide, we will visualize AES-128 decryption, which also consists of similar round. Now let us compare the difference between AES-128 and AES-256. AES-128 is faster and more efficient than AES-256, as AES-128 consists of 11 rounds in total, while AES-256 consists of 15 rounds. AES-256 is more resistant to brute force attack than AES-128. This extra resistance is provided by greater key sizes and more rounds in the algorithm. AES-128 key schedule is stronger than that of AES-256. The key scheduling algorithm for AES-128 generate more variation in round keys, as in every key expansion a round key is generated. But in case of AES-256, one key expansion generate exactly to round key.